Hey everybody, welcome back to another vector statics worked problem video. In this video, we're going to solve a moment about a point problem in 2 dimensions. So this is a problem set up here. There's this sort of pink L bracket that's pinned to the wall at point B, so it can rotate up and down, and there is a force applied at point A in this direction at a magnitude of 800 newtons. And then the question asks, determine the moment of F, so determine the moment due to this force F about this pivot point B down here at the wall. Now anytime you encounter a moment problem, you should be thinking cross product, specifically R cross F, where R represents the vector from the point of rotation to the point of application of the force, and then the force, of course, is a force vector. So in this case, the problem setup, what we're actually asked to find, the moment of point F, we can express that as m sub b, and keep in mind that moments about a point are always vectors, so we need to put the overbar above the m here. Now later on, when we do examples about moments about an axis or about a line, that is actually a scalar quantity, but we'll get into that later. For now, anytime you see moment about a particular point, you should be thinking that you need to produce a vector. And that vector, of course, is equal to some r cross some f. This is always the form for solving for some moment about a point. Now, the key to this problem is to actually figure out exactly what this r is and to define this force as a proper vector. So again, the r in r cross f, that's always a vector that goes from the point of rotation to the point of application of the force. So in this case, the proper subscripts here would be r from b to A. So we need this vector that goes from B to point A. And then F, of course, this is a vector. What we were given is the magnitude of that vector. So it might be wise to put something like, F800, just to let us know that this is a force vector due to the 800 Newton force. So then from here, we just have to figure out what these two vectors are. And a lot of these problems tend to build upon previous concepts. So when we're trying to figure out the R vector here, in other words, R from B to A, this exercise will feel kind of similar to when we were calculating unit vectors for force decomposition in 3 dimensions. One of the first steps in that process is to define the vector from, say, point B to point A. The way to think about this, again, is to pretend that you're standing at point B and then figure out how will you get to point A as you walk along, each of the coordinate axes. Okay, so standing at B, to get to A, we do need to travel in the negative x direction by an amount negative 0.2 meters. Because again, we're starting at a more positive x coordinate and going to a more negative x coordinate. So A is further to the left than B, so we're going in the negative direction. And then from B to A in the y direction, we need to go positive 0.16 meters. So, and this is our R vector. Very straightforward. Just 2 components. This is a planar problem. I'm starting with the planar problem because when we do go into 3 dimensions, the process is exactly the same. So getting our bearings in 2 dimensions, going through this process here, it'll set us up really well for when we start doing moments about points in 3 dimensions. So looking at this green force right here, right, that's a vector, and it's got some component in the x direction and some component in the y direction. Now, this is a 2-dimensional problem, so there's really no need to involve the lambda approach where we've got the unit vector that points us in the right direction. Typically, we'll use the unit vector approach for when forces are in 3 dimensions, and it's less obvious how we can use basic trigonometry to decompose the force. In this case, we've got a 2-dimensional force. So, if you consider F as a hypotenuse of a right triangle, the green line, the 800 Newton force, that's essentially the hypotenuse of that triangle. So the horizontal component, if 60 degrees is measured with respect to the horizontal component, that's just going to be our 800 Newton hypotenuse times the cosine of 60 degrees. So that's how many newtons will be pulling in the x direction right there. And then of course we've got another 800 sine 60 newtons. So that many newtons is going to be pulling straight up in the j direction, right? So again, our force decomposition, there's always some piece of the green force that's pulling straight to the right and some component of the green force that's pulling straight up. That's what these 2 components are. Okay, so now we have our R and we have our F. Now all that remains is to calculate the cross product, because earlier in the lecture we derived essentially that moments about a point can be expressed as this cross product R cross F. Now when you're actually solving this mathematical equation, there are many ways to actually do the cross product math. And one of the more straightforward ways, in my opinion, is to take the determinant approach. Okay, so what this means is we're going to take the determinant of some 3 by 3 matrix. For moments about a point, the matrix is relatively straightforward. In the top row, you've got each of the 3 unit vectors, I, j, k. The second row of the matrix is the components of RBA. So it'll be minus 0.2 meters, because that's the I component, 0.16 meters, that's the j component, and 0, there is no k component. Similarly for the force, you got 800 cosine 60, that gives us 400, and then 800 sine of 60, if you evaluate that on the calculator, you get 693 newtons, and then there's no k component. Okay, so we just need to take the determinant of this 3 by 3 matrix. There's a couple of methods that I outlined in class for how to do this. Probably the easiest way is to do the sort of cross out row and column method. What that entails is you pick one of these. We'll pick the first unit vector I, cross out that corresponding row and column, and then multiply that by the determinant of this 2 by 2 matrix here. You isolate j, cross out that row and column, and then take the determinant of this 2 by 2 matrix comprised of these 2 columns, and then there's a negative sign on the j term. And then of course you'll do the same thing for the k. So you'll isolate k, cross out its row and column, and then take the determinant of this 2 by 2 matrix and multiply by that unit vector k. So when you put all that together, you get negative 203 newton meters in the k direction. If you consider what this means, this is essentially a 203 newton meter torque or moment that's going in the negative k direction, so into the board. Now if you consider our right hand rule, if you were to run your fingers along the vector from B to A, so run your fingers along this vector, and then curl your fingers in the direction of the force, your thumb would be pointing into the screen, and that's what this indicates down here. So the vector corresponding to the moment about point B is actually a vector pointing straight into the screen. And one way to think about that is that vector, okay, so m sub b actually appears on this first diagram essentially here as a vector going straight into the board. According to our right hand rule, the way that your fingers tend to curl is the tendency of rotation of the object due to that 800 Newton force. So, if you apply an 800 Newton force at point A, this bracket would tend to rotate sort of clockwise and up and to the right. And that's the same direction as indicated by our moment. So the moment vector m sub b, you can almost think as it's sort of the axis of rotation that the object would rotate about given the applied force. So it's another way to think about that. Okay, but anyways, there you have it. That's a moment about a point problem in 2 dimensions. What we'll probably do is do another video of this same process, in other words, moments about a point, but we'll extend it into the 3rd dimension. And hopefully what you'll see is that this sort of matrix approach where you've got the 3 by 3 determinant, that totally scales into the 3rd dimension. So hopefully by applying this process in 2 dimensions, we've set ourselves up really well for doing moments about point problems in 3 dimensions. Anyways, that's going to do it for this one. If you haven't already, go check out the videos on our YouTube channel. There's over 600 videos, and these are videos designed for the specific classes in this curriculum. So if you're a student here, it's a really great resource for all the classes that you're taking currently. If you're not a student here, that's okay too. Our videos are free to the public, open for everybody. Feel free to check them out if you have a chance. Thanks again for watching. Thanks for subscribing to our channel here at Cal Poly Pomona, and we'll see you next time.